Hi, good morning. This is first tutorial. So we will be solving 8 questions today. I think the screen is visible. Our first question is, in FEA, the solution is said to be converging when the element is converging to a point, residue is tending to zero, order of shape function is increasing, number of element is increasing. So first of all, here convergence is mentioned and that too of a solution. So first we have to look at what FEM actually do. So let's say we have exact solution as given here, and we are approximating it using finite element method. So the dashed line is the exact solution and the bold line is our linear approximation of finite element method. And if we enlarge it, we will see that at different nodes we are approximating using a straight line, and in this straight line you can see that there is some residual left which is denoted by this red area. In the second, in the first subpart of the domain, we see that there is very large red area. In second, there is very little red area, and in third, as well as fourth, is negligible, and five too, and again in sixth, there is red area. So here we can observe that when there is a lot of curvature, then we see that it is having very large residue, and if we mark residues here, so these are also residues, which is just the difference between the the approximated solution and the exact solution. And what is happening here? Here, what is happening that this exact solution is very near to the approximated solution, because when we take very small element, it will be the exact solution is tending to become a straight line. But it doesn't happen every time. Wherever the curvature is very large, then we need some other techniques to reduce the residue. So the solution is said to be converging when the residue is tending to zero. We know that the solution we obtain from finite element analysis is always an approximate one and not exact. However, it is possible to reduce error and residual to minimum acceptable level, and when this happens, we say that solution converges. So there are techniques by which we can reduce these residuals and errors, uh, and then we will say that solution is converged. So this clears our first question. In FEA, the solution is said to be converging when we'll look at the other options also. Element is converging to a point. See, any element won't be converging to a point because element we are describing the domain, and those domains cannot converge to a point because actually we have already described it. Okay, so the thing is those values which are there in the element, those have to be minimized. The errors have to be minimized. Now second is order of shape function is increasing. Then also yes, so this can be our answer that order of the shape function is increasing and number of element is also increasing. But what these two do is it gives our residue tending to zero. So our mean answer should be the residue is tending to zero, but the sub answers can be order of the shape if it's increasing. Then also sometimes the convergence can be achieved, and also the number of elements if they are increasing, then also convergence is achieved. But here we are telling about the solution of the convergence of solution, and so it's not like when order of the shape function is increasing, so we are increasing up to a very large number, and then we will say that the solution is converged. Actually, it has an optimal value where which we can uh, balance between the accuracy and the conversion. So hence these two statements are wrong. The order of shape function is increasing and number of elements increasing. We'll look at the next question where we'll get more depth into how order of the shape function and the number of elements influence the conversion. So next question is which of the following will decrease the error? The first one is by increasing the order of the shape function or increasing the number of decimals in numerical value or increase the number of elements or all of the above. Now again we'll come to the same scenario where there is the exact solution as given as this. Let me mark question number 1 is done. So that in video we can track the speed and kind of get which question you want to do. Also I will be sharing this in form of PDF. Now yes, so we'll take the same scenario, and here we have um, approximated the function using linear elements. But let's see if we have little bit curved elements. What do I mean by that is as such, this thing is also curved, and see it fit nearly perfectly into it. So these are the curved elements. So this is the curved element and it fits into it as compared to the linear element which I will draw here. These were the linear elements. You can see in 1 and 6, apart from subdivision 1 and 6, it's nearly matching, like it's acceptable. But in 1 and 6, there is a residue which is handled using the order of the function. So the curvature is the order of the function. As you can see, it has a 3 point. It has a 3 point. Then it's called quadratic element. So 3 control point. One more method by which we can achieve this accuracy, or you can eliminate the error, is via distillation, more distillation. So it's called refinement, and it's called mesh refinement, or edge conversion, or edge refinement, where what happens is we subdivide the division, and then, as you can see here in this graph, we have subdivided the domain, and now I am putting the linear elements. So these are the linear elements. So as compared to the first case, where there were a lot of red areas, now we have very less red area. Let me show which red area I am talking about. Only this red area, as well as this red area, is only there. So as compared to the first situation, the red area is now decreased. So we can conclude that from more refinement of mesh, we will achieve, or we will get less error. We can look at in the form of equation also. So error is defined as the exact solution minus approximate solution, and which is given by this relationship if error is less than or equal to C, which is any constant, H, which is the degree of mesh refinement, power P, which is the order of the polynomial. Let me write down thing. H refinement is also called mesh refinement, and H convergence also. Similarly, P convergence is nothing but order of shape function. And previously it was linear element, or it's just denoted by the straight line, but now it is denoted by the quadratic line. So upon increasing the number of elements or defining the mesh, we can achieve accuracy, or we can reduce the error, as well as upon increasing the order of the shape function, we can again reduce the error. Now there was third point, that increasing the number of decimals in the numerical value. What does that mean? It actually means that upon increasing the number of decimals in the numerical value, we increase the arithmetic precision. Like, um, you have heard about the approximation errors. Those are errors which accumulates in time, or in a calculation, when we don't give proper attention to the rounding of the array. So what we do is, for one, if we have to subtract two numbers, let's say one is 8.145 and another is 8.0, 2. Okay. Now if we subtract these two numbers, we get here 3, here is 6, and 0, so it takes 0.068. And let's round off these numbers, round off one digit, so it will be 8.1. So 5 becomes one more digit, so like we can write it 8.15 and 8.08. Now let's subtract them. 87, so 0.07. Now upon rounding off, we see the difference is now having a difference in it. So it's like there's a difference of 0.003007. So this is what we call as round off error, and actually exists. So every machine or every computer have a machine epsilon, so which take care of this rounding of errors, because there is a smallest unit which a machine can understand. So while we are calculating in our system or in our calculators also have a machine system. So what we have is we we doesn't get this error, but if we round off these numbers and then we calculate the quantity, then we get these errors. So these errors are reduced if you take very large number of decimal places, but which is only practically possible in system, and because manually you cannot take all the numbers and put them into calculation, and then so it will be a lot of number crunching. So, so our answer will be which of the following will decrease the error is increasing the order of the shape function, correct, increasing the number of the decimal in the numerical value, correct, and increasing the number of elements, correct. So all of the above. Now we move on to the third question. Now our third question says, which of the following statement is true about finite element analysis? So first is the residue obtained equals 0. Second is the solution is exact. So I will cross this out because we are approximating the solution. Now solution is exact is boundaries. We look at it, what it means. It's an analytical technique. So no, it's a numerical technique. The two options are already crossed out. First, the solution is exact. No, the solution is numerical solution. It's the approximate solution. And it's an analytical technique means no, it's a numerical technique. Now, regarding the residue becoming 0. Now, if we take very small element here, let me enlarge it. Okay. So we are taking very small element, let's say this element from here, and we are enlarging it so that these two endpoints are denoted like that. Now we know that the exact solution will have some curvature, right? And whatever we are approximating will be different than that exact. So there will be always there will be a residual. Uh, so it's upon us to which accuracy we want. So we can ignore these red elements. So if there is no red element, then we achieve exact solution. But we are already discretizing and then we are approximating using some our own assumed solutions. So hence these residues are always there. So regarding residue obtained equal to 0, this is also a wrong statement. Now from the from this question, now we can understand the only solution is very solution exact to boundary. But what is the explanation of it? So finite element method is a numerical method. It's a tool that is a numerical method and it assumes the piecewise continuous function for the solution and obtain the parameters of the function in a manner that reduces the error in the solution. Now, boundary conditions are always input for the system and solution is exact at the boundary. Now, let me start with formulation. So we have governing equation and we try to, which is in the strong form, and we try to find the weak form. Okay, and here there is some boundary condition provided. So these boundary conditions ensure that ensure that solution is exact. Sorry, let me share my. Okay, it's already shared. The solution is exact at boundary. Let me put my phone to open. Alright, so let us revise the question again. Which of the following is true about finite element analysis? The residue obtained equals 0, so false. The solution is exact, false. The solution is exact, the boundary is true. It's an analytical technique, false. Alright, so we are done with question number 3. Now moving on to question number 4. Now 4 says the error the integration of error into a weighting function is, is used to finding solution of the problem using FEA. And if uh, is to represent the domain and what is W stand for. So we have the option error function, residue, coefficient, and weight function. So the solution is weight function, but let me explain this um, terminology for you. Like how weight function, what is a weight function actually? Okay, so to understand that, first we have to look at something called fundamental lemma of calculus of variation, which states that So it is from um, calculus of not calculation of variation, calculus of variation. The calculus of variation is a subject which was uh, very in early time it was the only thing which give us the optimization of the functional. So and all the modern FEM and lot of other theories came out from like the base is here only because it's a uh, optimization problem. So everything is an optimization problem of its own if we consider software. So hence so there is a fundamental lemma that if gx is continuous function, let's say in x naught, x, x1, and there is one more condition given that if integration from x naught to x1 of the gx into hx dx is equal to 0, where hx is any arbitrary function in the same interval with h of x naught is equal to h of x1 equal to nil. Okay, then what we can say about the system is g of x is equal to 0 at every point in the interval so this is there if gx is any continuous function, okay, which is from x naught to x1, and if this condition is given where hx is the arbitrary function in the same interval hx naught is equal to hx1 is equal to 0, then j is equal to 0. So if that is there, then this is there. Now, what does it physically mean? It physically means that, let's say, let's go bottom to up, that if gx is 0 everywhere in a system, then if you multiply it with some hx whose boundaries are 0, then the integration of x0 to x1 that also becomes 0. So now we can correlate with our, it's called weighted residual form, it's called weighted residual equation. So this is our weighted residual. So can you identify which one is weight and which one is our error, or Now which one is our residual? So you can see that this is our error and this is our weight function. So weight function should satisfy that it should be in the same interval, it should be 0 at the boundary. Apart from that, it will give that error is 0. And now error is 0 everywhere. So that's what we need, right? That error becomes 0 everywhere. So hence this calculus of variation is very useful and it's kind of base of finite element method. And now in our case, if let's say u tilde is the approximate of u, then error is defined as u minus u tilde, and this is our weighted crystal form. So there could be lot of weights. So weight can be anything. So depending on the weight, it becomes a different method altogether. For example, if weight is equal to x minus xi any point which is in the domain, then this method becomes collocation method, and this weight function is also called test function. So I hope it is understood by you. Let me go again. The fundamental lemma of calculus of variation, which is very important in finite element method, is that if g of x is continuous function in let's say x naught to x1, and if a weighted residual form is given such that integration from x naught to x1 of gx into hx dx equal to 0, where hx is an arbitrary function. So arbitrary function meaning it can be anything, right? So we have the choice to take whatever we want, but this will satisfy, it should satisfy that at x dot is equal to x1 is equal to 0. So that is the only condition which is required by this what we call weighted function, and then gf is equal to 0 at every point in the interval. So this is the base of finite element method, by which weighted residual method, and the base of the weighted residual method is this fundamental lemma of calculus of variation. So this completes our question number 4. Now moving on to question number 5. Okay. So in FEA, when can we use axisymmetric governing equation? So axisymmetric governing equation meaning, what is meaning of axisymmetric? First we have to look at that, and then there are points that cross section is axisymmetric, boundary conditions, material properties, loading conditions, all of the above. Alright. So let's dive into what is axisymmetric problem. It is actually axisymmetric problem to the equations governing physical processes is in general. Alright. in a cylindrical geometry. So the important word is cylindrical geometry. So it should be defined as cylindrical geometry. The first point being these equations governing physical process in the cylindrical geometry are described analytically in terms of cylindrical coordinates. The first thing is they should be defined in cylindrical coordinates. Next is now this is important. The geometry. Let's say we are analyzing a can. Let's say this is a can, and we are analyzing that. So the geometry wise is a cylinder. So that is one case. Then loading. Now there are cylindrical loading such that at this radius from every side the force is coming, such as pressure or internal pressure, or even boundary condition. There material properties. These are independent. These are independent of the circumferential direction of theta coordinate. Circumferential direction theta coordinate. What is theta coordinate? So this angle, right? So it should be independent of this theta coordinate. So that is the meaning of axisymmetric problem. The problem is called as axisymmetric. Problem is called as axisymmetric. And the governing equation becomes 2D. So this gives us a benefit to convert this problem into 2D, 3D problem into 2D, because uh, we have not dependency on the one coordinate, which is theta coordinate. So only left R, R and Z. So what was R? R was this and Z was this. Okay. So this is called axisymmetric problem, and this will be all of the above. So there are a lot of problems, such as pressure vessel, as well as even the hyperloop tube. So there what happened that we have pressure generating in a symmetric way, and even the boundary conditions are applied such that it is not dependent on the zeta coordinate. Material properties are also such that it is not dependent on the zeta coordinate. So in that case, what we do is we map the system into a 2D coordinate system, which is R and Z, and the solution is pretty accurate. So let's move on to the next question. What is the number of nodes of the domain when it is discretized into n linear 1D elements? So this is the same case which was mentioned in the first question. So we have exact solution as a dotted line, and we are approximating using linear elements, and let's count out how many. So there are 1, 2, 3, so 6 divisions, so 6 discretizations, and how many nodes are there? Let's calculate that. So 1, 2, 3, 4, 5, 6, 7. So if there is 6 discretized, then 7 nodes are there. So this gives us solution of n plus 1. Now next question is, when discretization of domain in FEA, maximum error occurs when shape function is, so as compared to the quadratic and linear, we got the feeling that the quadratic is giving less error. So conversely, we can say that linear element gives maximum error, and now there is something called quadratic, by which we have uh, 3 points, or we will say the control point. Let me just define what. Mhm. So as you can see on this iPad, this pencil gives us the spine line, and we have an option of a quadratic line. So this is a quadratic line having 3 control points. Also we have linear. So this is for linear, having 2 control points. Similarly, there is something called constant. Constant is nothing but a point, and it is denoted like this. So we cannot change its slope. Let me define it. This is 1, and here is second, and this is control point. It is 3 control points. This is linear element. and this is constant element having only one control point. So from intuition, we can say that constant element should have at least a maximum error. So let me put that. So let's say instead of the let's say instead of this we are using constant element. So this is how the constant element will look like. Now if we talk about the errors, these are errors are now very much more than the linear element. Let me show which error I am talking about. So the error. So this is using the constant element. You can see the red shaded area are very much more than the constant, oh sorry, linear element. This is constant element, this is linear element, and this is quadratic element. You can see here all the elements are quadratic, having three control points. Alright, and here the elements have two control points. Okay, so let's solve our last problem. So it is said that in a 1D quadratic element, it's a quad element, how many nodes are present? This already has covered this. That this is our quadratic element. So let's say it has, let's say this is our exact solution. The exact solution, and this is approximate of this exact solution in a quadratic element. Okay, so let me change this color. So now I'm fixing the endpoint, right? And as you can see, now this exact solution, I can put it like this or like this. I put it anywhere. This is not equivalent to the exact solution. So I need more higher order. For the close fit, this can, as you can see, like, up to this point I can have, but then after that it has a having huge error. So let me show the errors. So these are that errors. Okay. So this completes our discussion on for the first week. So also I have a proof of uh, this calculus of radiation in the fundamental lemma of calculus of radiation. So I will just write it down here to this page. So it's a proof by contradiction. By contradiction. Contradiction means we will first say that the statement is wrong, and then finally it will become everything it will also become wrong. So then we'll say that things that was correct, so this will be also correct. So let us suppose that the function gx is non-zero, okay, and positive also. There is an interval and there is a subinterval. The interval is same as x0 and x1, and subinterval is a and b. Alright, so we are saying that this gx is non-zero and is positive in some subinterval. Now, since hx is arbitrary, we can set to be any function. So we are setting this h equal to 0 and x minus a and b minus x. We can do that, right? Since it's arbitrary, we can take any function. This is a discontinuous function, but the boundary condition like at x naught it is 0 and at x1 it is also 0. Now we look at the integral. Now, everywhere it's 0, so only from this point to that point it won't be 0, and the value will be like this, now which is greater than 0, right? Now at x equal to a, what is happening? And x equal to a and x equal to b, so it is 0, and apart in between it is positive. Okay, cool. To this point. Therefore, this lemma is proven as the only way for the integral over the entire interval to be 0 is that the function gx is 0 everywhere. Okay, so this complete our proof, and okay, so I'm ending the class now.